editor says, "We regret to inform you that your paper was not accepted for publication as is. However, as I see value in the proposition, we invite you to submit a revised version along with the response letter to the reviewers."
Do you think we have a chance? One reviewer was very challenging, to say the least.
Yeah, difficult. Look, for example, over here, they say, "The authors seem to lack some fundamental knowledge about generative models needed to perform this study. Yet, there are no details to understand what this refers to."
Strange.
You seem concerned about something.
We need to review our paper, but one reviewer challenges our understanding of generative models.
I know someone who can help you to get to the bottom of the rabbit hole.
Where can we meet this person?
Follow me.
Well, thank you so much. Mint told us he could help us with a revision for our paper. We got some really harsh comments from reviewer number 2. These comments we don't know how to rebut.
Not knowing the truth is like living inside of a prison in your mind. It allows other people to pull a whole world over your eyes, preventing you from seeing the truth.
What truth?
The liberating truth of generative modeling. Take the blue pill and live as of now. Take the red one and I'll show you the truth. Follow me down the rabbit hole and I'll show you how deep it goes for generative models. Remember, all I'm offering you is the truth, nothing more. Now the red pill will help us track your signals to where we are going. So let's go ahead.
Oh, HDMI? I don't know where you can plug that into.
What? That's to plug into this.
Oh, I see. What is this place? Where are we?
Is this maybe the Matrix?
Beyond that, welcome to the Tensor. Here you will receive training. Let me introduce you to the architect, an advanced program we developed for that purpose.
Welcome. I understand you are here to train yourself in the arts of generative models. Well, get ready. You are probably familiarized with models that can learn to make predictions. Their goal is to learn from data and make predictions on new samples. These models belong to the family of discriminative models. In contrast, generative models aim at creating models that describe a data distribution. Generally speaking, they aim to model our world. For this, generative models rely on the 2 steps of density estimation and sample generation. Generally speaking, the density estimation step aims at modeling the probability distribution of a data set, while the sample generation step uses this model to generate new samples, hence the general name of generative models.
So, generative models are like data creators?
Indeed, generative models can be seen as data or sample generators. But generative models can be used for other purposes as well. For example, generative models can be used to unveil the distribution of representative features in a data set, which can be insightful to better understand what a model captures as being important in a data set, or to unveil potential biases in a data set that can negatively affect downstream tasks.
That's great, but maybe can you explain in more detail what the density estimation and sample generation steps are?
Sure. For this, it is useful to look at the 2 most popular approaches in generative modeling to perform density estimation, either explicitly or implicitly. The first one is called Variational Auto-Encoders, or VAE. A variational autoencoder models data distribution in an explicit way. To better understand VAEs, it is useful to first look into autoencoders. Autoencoders are neural networks trained to learn a lower dimensional representation of data. This representation is learned via an encoder network, whose objective is to learn meaningful features of the data, also called latent variables.
Why do we want to reduce the dimensionality?
Excellent question. Basically, it is a distillation process of the most important factors of variation of the data. The dimensionality reduction can act as well as a denoising operation and provide factors of data variation that generalize enough so they can be used for generative purposes.
And how do we learn these meaningful and compact latent variables?
To do that, a second network called decoder is used together with the encoder to reconstruct the input data. The process then consists in inputting training data into the encoder, obtain corresponding latent variables, and then use them in a decoder to reconstruct the input data while minimizing a reconstruction error, which is typically measured at the pixel level. The rationale behind doing this is that good latent variables can describe the training dataset such that individual samples can be reconstructed to a high degree of fidelity. Once the training is finished, we no longer need the decoder and can use the encoder part to generate latent representations for input samples. Auto-encoders are designed primarily to reduce dimensionality of input data and extract meaningful features. To generate new samples, variational autoencoders were then proposed. Building on autoencoders, variational autoencoders also follow the same idea of using an encoder, a decoder, and minimization of a data reconstruction objective. To generate new samples, we focus here on a decoder model able to receive latent variables as input and output a new generated sample. However, differently from autoencoders, variational autoencoders impose that the latent variables follow a certain data distribution, for example, a Gaussian distribution. In addition, a variational autoencoder models probabilistic generation of data, so their outputs are modeled as mean and diagonal covariance parameters.
But why are they called variational autoencoders?
Good question. This formulation of variational autoencoders lead to computational intractability in practice. Hence, it was proposed to approximate the derivation to a computationally tractable lower bound. This is why the term variational in VAE models.
So how do we train and generate samples with this approximation?
The process is similar to an autoencoder, but in a VAE model, we encode a training sample into mean and covariance latent variables, which are then used to draw a latent representation from a Gaussian distribution. The training process aims at optimizing two aspects. First, a reconstruction loss, as done for autoencoders, and a regularization term enforcing the latent distribution to follow a Gaussian distribution. This second term enables learning a smooth latent state representation of the input data, which enables smooth interpolation between samples.
So, what are then the pros and cons of VAEs?
VAE models are easily trained and allow for a principled and explicit methodology to generative modeling. However, in comparison to other approaches, VAE tend to generate samples of relatively lower quality.
I know VAEs.
Go back.
What was the second approach?
The second approach uses an implicit way of modeling density estimation. These are called Generative Adversarial Networks, also called GANs.
Why implicit?
In contrast to VAEs, generative adversarial models employ a two-player game strategy to indirectly do the density estimation step. The two players are called discriminator and generator and compete with each other in a process called minimax, where the discriminator aims at detecting samples generated by the generator, while the generator aims at improving its sample generation to fool the discriminator. In the original formulation, during training of a GAN, an objective function is built such as the likelihood of the discriminator being correct on synthetic samples is minimized. Or in other words, the generator effectively fools the discriminator, and the likelihood of the discriminator in detecting real samples is maximized. These two steps are performed alternately using gradient descent and ascent. In practice, however, it is more effective to maximize the likelihood of the discriminator to be fooled. The generator starts with random noise as latent vector to generate new samples, which are then passed on to the discriminator, which classifies them into true or synthetic. The objective function is calculated based on the performance of the two players, and gradient ascent is used to optimize the model parameters.
The min-max game sounds like fun.
As a matter of fact, training GANs can be very difficult, as it is crucial to find a balance between the ability of the generator to fool the discriminator and the ability of the discriminator to improve its detectability performance. One specific issue here is called mode collapse, wherein the model converges to a solution point where the generator narrows down its outputs to a given sample or limited range of samples, where the discriminator is always fooled, and it can't improve anymore.
Are there ways to prevent mode collapse?
Much research has been dedicated to improve the convergence and stability of GAN models. Some effective initial solutions worth mentioning include using mini-batch discrimination, where the generator is encouraged to produce more diverse samples, or using feature matching where the loss function of the network is changed so. Other regularization approaches such as weight clipping, gradient penalty, or spectral normalization are used to prevent discriminator updates from becoming too extreme. Another stochastic approach involved injecting noise into the input of the generator. This can help prevent mode collapse by adding stochasticity to the generated samples. A data-centric approach to improve stability is to ensure that the training dataset is diverse and contains examples from all the modes you want the generator to capture. Mode collapse can occur if the dataset itself lacks diversity. At this point, it is important to remark that mode collapse is a common challenge in GAN training, and there is no one-size-fits-all solution. Research in this topic is still very active. In practice, it is a combination of experimentation and experience. Monitoring the generator and discriminator loss functions during training for sudden spikes or drops in loss values can be indicative of mode collapse.
Are there other variants of GANs that have shown improvement over the vanilla one?
Many variations of the vanilla GAN have been proposed over the years. Here are a few relevant ones worth mentioning. DC-GAN. A DC-GAN, or Deep Convolutional Generative Adversarial Network, is a type of generative adversarial network. It was introduced by Radford and colleagues in 2015. DC-GAN has become a foundational model for image generation tasks due to its ability to generate high-quality and realistic images. These are the main differences between DC-GAN and the vanilla GAN. DC-GANs use strided convolutions in the discriminator and transposed convolutions, also known as fractionally strided convolutions or deconvolutions, in the generator to control the spatial resolution of feature maps. DC-GAN adopted batch normalization layers to stabilize and accelerate training. They help normalize the activations within each layer, making training more efficient and combating issues like mode collapse. DC-GANs also adopted leaky rectified linear units, called leaky ReLU. Leaky ReLU allows small gradients to flow through, which can help mitigate the vanishing gradient problem. The generator of DC-GANs typically uses a hyperbolic tangent or sigmoid activation function in the output layer to constrain the generated pixel values to a specific range. The discriminator of DC-GANs has a single sigmoid activation in the output layer, which produces a probability score indicating how likely the input image is real or fake, instead of a binary as used by vanilla GANs.
Do DC-GANs solve the issue of mode collapse?
While DC-GANs implement several strategies that can palliate mode collapse, it can still happen. A notable variant of GANs proposed to have better stability against mode collapse is the Wasserstein GAN, or WGAN. Wasserstein GAN is a type of generative adversarial network that uses the Wasserstein distance to measure the difference between the distribution of real and generated images. Its key features are using the Wasserstein distance for the loss function provides smoother gradients and helps to alleviate issues like mode collapse and vanishing gradients. In WGANs, the discriminator is called a critic and is not trained to classify, but to provide a rating or score for the inputs. This score does not have to be between 0 and 1. GANs introduce weight clipping or gradient penalty to ensure Lipschitz continuity. Lipschitz continuity is a mathematical property that describes how smooth or regular a function is, which facilitates the convergence of the gradient-based optimization of GANs. It has also been shown that the loss value in WGANs correlates better with the quality of generated samples compared to traditional GANs. This makes it easier to track the progress during training. Remember that while WGANs address some issues present in traditional GANs, they come with their own set of challenges and considerations, such as computational cost.
Is there a way to control or guide the generation process?
Yes, this is referred to as Conditional Generative Adversarial Networks. C-GANs are an extension of the original GAN framework. While traditional GANs generate data samples from random noise, C-GANs introduce the concept of conditioning, allowing for more controlled and targeted data generation. The condition is injected in GANs as an additional input channel or feature in both the generator and discriminator networks. This condition can be in various forms, depending on the specific application. For example, the condition can be an image where the goal is to generate a corresponding image in another domain. This is also called image-to-image generation. Similarly, in text-to-image generation, the condition can be a textual description, where the goal is to generate an image that matches the description. Another difference with respect to GANs is that, in addition to the adversarial loss, C-GANs often include a conditional loss term that measures how well the generated samples match the provided condition. This loss encourages the generated samples to be not only realistic but also to align with the given condition.
Can you teach us more about the different C-GAN methods proposed so far?
Sure, if you want to stay in the tensor for the next weeks, as the list of proposed methods has grown over the years. But there are some very good resources out there on the so-called GAN Zoo, where you can dive into further details, should you want to know more about specifics.
What about using GANs for medical image computing? Does it work?
GANs have also been used in medical image applications. They have been used for several scenarios, including, for example, image denoising, modality conversion, modality or MRI sequence imputation, or in super resolution, which is about generating higher resolution images. Image in painting in, for example, CT applications where metal artifacts need to be removed, or counterfactual generation where a conditional GAN can be used to transform an input image conditioned on a different class. GANs have also been tested for image segmentation, but the effectiveness of other architectures and the training stability and convergence of GANs mentioned before have precluded their wider adoption for segmentation. Probably the most notorious use of GANs in medical image applications is in data augmentation, where these models provide a more realistic type of data augmentation compared to traditional augmentation techniques based on image manipulations.
But I heard about something called diffusion models. Are these GANs too?
Diffusion models are also generative models, but have a different working principle and training procedure than GANs. Diffusion models are based on the concept of iteratively refining a random noise source to approximate the target data distribution of images. They work by progressively adding Gaussian noise to the training data until it becomes pure noise. Then, a neural network is trained to reverse this corruption process. This involves learning a series of conditional distributions that model how data evolves from highly noisy to less noisy states. Hence, they generate new data from pure noise by gradually denoising it. Diffusion models are likelihood-based generative models. They directly model the likelihood of observed data, aiming to maximize it during training. This contrasts with GANs, which use adversarial training to indirectly generate data by minimizing a divergence between real and generated data distributions.
Wait, this doesn't look good. I need to bring it back right now. It looks like an agent moving fast towards your direction. They are not known to be friendly. But this is weird. The perturbation happened in the tensor, but I can also see signal fluctuation nearby. Like it's happened
in the real world? Mr. Agarwal, Miss Anderson, I came here to learn about your pitiful attempt to overcome my review.
Are you reviewer number 2?
Yes, you can call me that too. I'm here to finalize this review, right here, right now. Let's see if you can dodge my comments.